Okay, welcome back everybody. So we're moving on to the last section in chapter 2. It's called the Fourier transform in d dimensions. And of course I've kind of really talked about the Fourier transform already for the last 2 videos, but I was giving it the name the Fourier series transform. And in this case we're going to eliminate that word series to maybe what a lot of people think of as the Fourier transform. And so the difference mainly between the Fourier series transform and the Fourier transform is that the Fourier series transform in d dimensions we had defined over the hypercube of length 2 pi. So we take some hypercube in d dimensions, length 2 pi, centered at the origin. What we can do to recover the Fourier transform that most people refer to when they talk about the Fourier transform is give the hypercube side length the name L. So hypercube of side length L, and so it's going to be getting bigger and bigger if we allow L to go to infinity. So we're going to say, hey, now it's twice the size it started, 3 times the size, 1,000,000 times the size of the original. And we're going to let that hypercube get bigger and bigger, and once it encompasses all of space in the limit, we're going to say that it converges to all of Rd, the d-dimensional space. And in fact, this is important because now the shape actually of our original domain doesn't matter, because as long as our domain was occupied some amount of volume, if we increase the volume in every direction by an equal amount and take that to infinity, we're still going to encompass all of Rd. So this truly is invariant under all invertible transformations on the d-dimensional vector space. And so that really makes this a very useful and universal fundamental tool for us to use this Fourier transform, moving from just a finite interval minus pi to pi into the infinite interval of all of R. So let's see what this looks like. Basically, the price we pay, and I don't even know if it's something to pay because it's almost just as easy to work with, so I'll put that in quotes. The price we pay to increase the size to all of Rd is an integral instead of a sum. And this is for reconstruction. So with the Fourier series, you would reconstruct your function using a sum. In the Fourier transform, you reconstruct the original function using an integral. And so that's what's right here. This is the analog to our reconstruction. This is the analog to the Fourier series over an infinite domain. So what you can see here is I still have phi hat, but I'm giving myself the variable y as a vector in Rd instead of n as a vector in Zd. And I know a lot of you maybe didn't like working with Zd anyway, and so it's probably easier for you to work in Rd. So now we have a variable y in Rd. That's what goes into phi hat, and then my reconstruction, instead of having a sum here, right? In the past we had a sum, we said n was in Zd, and then we didn't have any sort of a measure like that. In this situation, now we have an integral over all of Rd, and we have our volume measure. And so I've indicated putting a y here to say this is the volume form with respect to the variable y. We're not going to integrate over x, so this is really just dy1, dy2, ... dyd. So that's the volume form of the reconstruction. What does the Fourier transform itself look like? Recall the Fourier series transform before was just the term with the hat on it as a function of n. Now this is a function of y, and we're able to compute it exactly how we computed the other one before. Nothing has really changed except I guess technically a d over 2 instead of a d there. That's just because I absorbed a d over 2 into the other term. Make things a little bit more symmetric, right? So in this situation, everything looks super symmetric. And I don't mean that in the modern physics interpretation of supersymmetry. No, it just looks like, visually, we have a very, very well-defined symmetry. In fact, the only difference between these two is the complex conjugate. So that's really quite fascinating, that once we transition to an unbounded domain, the only difference between a Fourier transform and its reconstruction is a negative I in the transform and a positive I in the reconstruction. And this really hints at a very common property that's studied in mathematics called duality. So it turns out that the Fourier transform is its own dual, or it's called an involution sometimes. So So this is a very nice nice transform to define. Basically, if you got comfortable in the last section with the Fourier series, you should be very comfortable computing this Fourier transform. Just keep in mind that now your integral is happening over an unbounded space, and so you have to be a little bit careful about computing improper integrals where the bounds are technically limits. So you want to make sure that the limits converge. So the proof of this is actually really a nice proof. I won't go through it. It's exactly everything you would expect it to be when we set up this omega sub L as our L-sided length L hypercube. And then you take L to infinity. If you make the right change of variables, you end up with the sum. Let's go to the right section of the sum here. You end up with the sum occurring over a finer and finer mesh. So this is really a mesh in RD. So it occurs over a finer and finer mesh as L goes to infinity, and we have exactly, this is really delta V, and what we end up with is a Riemann sum gives the integral as L goes to infinity. And so you end up with a Riemann sum that your regular sum converges to a Riemann sum, which itself converges to an integral, and that's where we pick everything up that we want to. Then kind of the only special thing is that regularly you wanted to divide by 2 pi to the d power, and what I do is I just split that into 2 parts, because that is what allows me to have the really nice symmetry. You don't need to do that. In fact, a lot of definitions don't do that. You'll have to pay attention to the definition book by book, because some people do split it into both sides and other people leave it on the transform. Other people bring the whole term to the reconstruction. So you just have to be careful that you pay attention in any given book where the 1/2 pi ends up. But let's actually compute this, because that's probably why most of you are in the course, is to actually think about computing these. And so let's just do it in 1 dimension. I didn't split this section up like I did the last section between the 1-dimensional and d-dimensional, just because I think everybody got used to the d-dimensional Fourier series by now. So we're going to be fine just jumping right into the d-dimensional Fourier transform. But I do want to cover like a computation of a 1-dimensional Fourier transform first before we get into d-dimensional computations. So let's think about what is a square integrable function over an unbounded domain. What does this mean over unbounded domain? Well, let's think about it. It means that it's the same as before. It just means that now my bounds are minus infinity to infinity. When I square a function and I compute the improper integral, that this still exists and is finite. Okay, so this is what it means to be square integrable over an unbounded domain. That's exactly what you'd expect from before. This is kind of a very classic square integrable function. Let's verify that. I've got the verification right over here. So it's easily confirmed as square integrable since, okay, if I define my function, let's keep in mind, how do we integrate piecewise functions or absolute values? They're the same thing in some situations. So my piecewise function differs at positive numbers versus negative numbers. So I'm just going to split up the integral when I'm testing square integrability. So I'm going to split my integral. Here I'm testing square integrability. I'm splitting it at 0. And my function behaves differently on each side of 0. How does it behave differently? Well, one of them is a positive exponent and the other is a negative exponent. So now I've got both of those individually on the one half line and the other half line. I can find the antiderivative. As before, the antiderivative is dividing by the coefficient for exponentials. And here I'm going to divide by the coefficient as well. And what we end up with is 1/2 plus 1/2, and we get 1 over all. There should be an e to the negative 2x in this term right there. That's a bit of a typo. But we end up with 1/2 plus 1/2, so we get a total of 1. If I were to square this function and calculate the area underneath it for the whole line, you get a total of 1. So that exists, and that's finite. So this is definitely a square integrable function. Once I know it's square integrable, I know the Fourier transform exists. And so I can go ahead and compute the Fourier transform of f. I'm going to do it right based off of its definition. The definition of f hat is just, if I'm in 1 dimension, this d in the power of the 2 pi just becomes 1 because I'm in 1 dimension. And my integral over r to the d power is just the integral over all of the real numbers. And my volume form is just dx, right? There's only one variable that I'm integrating over. That's going to be x. And I'm just going to directly do what I did earlier and split my function where the piecewise function actually differs. I'm going to split it here at 0 and at 0. This should actually be 0 to positive infinity. That's another typo. 0 to positive infinity. So I split the function there, and I end up with two different exponentials, I should be able to integrate that exponential and that exponential individually. If I use my exponent rules, I can combine all of the exponents together. And then all I do is I isolate, okay, what is the term that doesn't depend on x? It's 1 minus iy. What is the term that doesn't depend on x? It's 1 plus iy. So that means when I find the antiderivative, I divide by those terms that don't depend on x. And then I compute the antiderivatives at the bounds. I'm just being clever about making sure I'm actually evaluating these at the bounds of negative infinity for x. So I'm plugging negative infinity there, and I'm plugging 0 in there. I'm plugging 0 in here, and I'm plugging positive infinity in here. And when I do that, both of the infinities actually tend towards 0 because that's e to a minus infinity, right? E to the minus infinity is 0. 1 divided by infinity there is 0. And so all I pick up are the 0 terms, those two, and then when you add them together, you get exactly that. So that looks ugly. The Fourier transform of a purely real function, right? That's a purely real function. The Fourier transform of a purely real function should be purely real. So I have to get a little bit clever about combining these. If I do that with common denominator, I'm going to common denominator this as 1 plus iy divided by 1 plus y squared plus 1 minus iy divided by 1 plus y squared. That's going to be my common denominator. These terms cancel and I get a 2 on top. My 2 on top I'm going to cancel with one of the square root of 2 in the bottom, and you end up with 2 over pi square root and then the denominator of 1 plus y squared. So that is the Fourier transform of e to the negative absolute value. So you compute it just like you would Fourier series transforms, just by computing integrals, and just make sure that you keep track of everything you need to. I'm then going to introduce the example in d dimensions, which is very important, of probably the most important Fourier transform in the world. This function is the most important Fourier transform in the world. This is known as the Gaussian. And in fact, I've normalized it. When you put 1 over 2 pi to the d over 2 out front, that's actually the normalized Gaussian. But it doesn't need to be normalized to satisfy the very nice property, which is the Gaussian is unchanged by the Fourier transform. This is like the fixed point. It's nothing changes about this function when I take a Fourier transform, except for the variable, which I should have changed there. But the only thing that changes when I take a Fourier transform of a Gaussian is that I'm changing my variable from an x to a y. We should actually prove that. I recover this still. We should actually prove that here. So we go through the computation. How am I going to do that here? How am I going to compute the Fourier transform of this? Well, I'm just going to write it out, but I'm actually going to expand. What does this mean? What does the absolute value of a vector squared mean? Well, by definition, the magnitude of a vector is every entry of that vector squared. And then you take a square root of it. But if I square that, it's the square root squared, so the square root and the square cancel. And the absolute value squared is just the sum of the squares. Okay, so really what's going on here is it's e to a negative sum of squares. There's my negative sum of squares. And then what is this inner product, or the dot product here? E to the I, y dot x. There's a dot product of y's and x's. This is e to the minus I, y1, x1, minus I, y2, x2, minus dot dot dot, minus I, y, d, x, d. That should be a minus. There we go. And so if I expand all of those terms out, then we end up with these, and then once again, I'm going to expand the volume form out, and then I'm going to use exponential rules to group everything in terms of its subscript. So there's all x1s, y1s, x2s, y2s, xd, yd, and then I'm going to group integrals according to their subscripts as well. So I'm actually, because that's a product form, and because thankfully there's no mixed terms here except for products, so I have a product form and a product of functions here as well, I can split these into individual integrals. So these are all integrals now in one dimension. It's just a product of integrals in one dimension. And we're going to try to compute them individually. So notice, actually, these are all Fourier transforms in one dimension of the one-dimensional Gaussian. So if I can show that the one-dimensional Fourier transform of the Gaussian is the one-dimensional Gaussian, then I can just completely do the opposite of everything and end up with the Gaussian I started with. So let's try to compute the Fourier transform of the one-dimensional Gaussian. So I've just fixed a subscript, calling my subscript j. J could be any of these. It could go from 1 to d. So I'm just computing any of these individually as this, and I would like to see if I can actually explicitly compute it. Let's see. So how can I tell what this integral should look like, this integral. What I'm going to do is something very clever, something that you're not going to be expected to necessarily know until somebody shows you that you should do it. This is, we're going to take a derivative of the Fourier transform, right? A derivative of my one-dimensional Fourier transform. I'm just going to say, by definition, my one-dimensional Fourier transform looks like this. And I'm going to take a derivative of it in its only independent variable, which is yj. And when I take that derivative in yj, it goes against the integral, but it pulls into the integral. And once it's in the integral, it sees the only term with a yj on it. So there's only one term with a yj on it. And when it sees that one term with a yj on it, it says, fine, I'll take a derivative of that. And it takes a derivative of that, and we get negative I xj, because that's what the chain rule gives us. It says, okay, chain rule says everything except for yj in the power comes out front. So the chain rule gives me a negative xj out front. And I can pull the negative xj over here and say, wait a minute, negative xj against the Gaussian is actually the derivative of the Gaussian in the variable xj. That's something very special. So negative xj multiplying the Gaussian is the same as the partial derivative of the Gaussian in xj. So now that I have a derivative here, I can actually use integration by parts, because I've got one term of my integral, which is a dv, and another term, which is a u, and I can rewrite this as uv minus integral v du. If I actually go through that process, we recover the following. This is uv minus v du. And if I simplify this, this actually simplifies to 0, because if I evaluate on the bounds of minus infinity and plus infinity, I've got an e to the negative infinity on both sides here, so this becomes 0, which means I'm only left with this term. But if we're really, really, really clever, this is actually f hat from the beginning. So the piece I put in red there, which is the same one as I just highlighted, that's actually f hat. And so what I've ended up with is that the derivative in y of f hat is negative y times f hat. So a derivative is equal to negative the variable times itself. I'm going to rewrite that. I'm going to give the variables some new names. The derivative in the variable is negative the variable times itself. Let's give it all some new names. What's actually going on? Z prime is negative tz. That's just an ordinary differential equation, and everybody knows how to solve it. All we need to solve it is an initial condition. What's the initial condition? What's the value when yj is 0 of f hat? Well, you can just calculate it. F hat of 0 is the integral of the Gaussian, and thankfully, since I normalized it, we just get 1 over root 2 pi out front, which means my initial condition of this z equation is 1 over root 2 pi. Therefore, I'm solving the ODE, the initial value problem. Z prime equals negative tz. Z at 0 is 1 over root 2 pi. Any of you can do this from the end of chapter 1. It's just a separable equation. The solution is a Gaussian, which means that the solution of f hat, the computation, this is the funniest thing, is that to compute a Fourier transform, we were just able to translate the Fourier transform itself into an ordinary differential equation, which was a separable equation, and we were able to solve that separable equation to give us what the Fourier transform looks like. So now we have the Fourier transform of the Gaussian in one dimension, in just the dimension yj, and so then I replace every single one of these individual Fourier transforms with the Gaussian in yj. So in the Gaussian in y1, the Gaussian in y2, the Gaussian in yd. I'm going to replace all of them with the Gaussians in y. And when I do that, here's my Gaussian, it should be in y1, in y2, and in yd. Here's the Gaussians in all of my y's. And then using exponent rules as well as power rules for all of these denominators, we can multiply those all out, and we see that's exactly the d-dimensional Gaussian that we started with. So that's really a very fascinating property about the Fourier transform, is that the Gaussian is preserved. But we're going to move on. I mentioned that the motivations of the Fourier transform the Fourier series transform applies to the Fourier transform as well, but we won't get into that. It's the same sort of motivations that I've already described to all of you. Instead, I do want to comment in the same way that the Fourier transform plays the same role in differential equations that the Fourier series transform did, in the fact that it diagonalizes the derivative. Now, I wasn't fully truthful in the way I said diagonalizes the derivative the last time. It diagonalized the derivative the last time over, bounded domains. And now when we have the Fourier transform, we're going to diagonalize the derivative over unbounded domains. So really, whether or not we use the Fourier series or the Fourier transform to diagonalize the derivative will depend on the domain at hand. And this is actually why these domains of omega are so important when we're solving PDEs, is because our Fourier series transform only applies to PDEs who have hypercubes as their domains, or at least the one that I introduced to you. So you can only apply those nice little differential equations properties we got to at the end of the last video to PDEs defined on the hypercube. And there's so many omegas that are not hypercubes that it is a little bit restrictive. Now, a very common omega, one also known as like the universe, is ideally unbounded. Nobody really knows, but like we treat it as though it's unbounded, which means that we can solve a lot of universal differential equations under an unbounded domain using the Fourier transform. Right, so this is where the Fourier transform kind of achieves some sort of more power over the Fourier series, is because the universe assuming as an unbounded domain is much more common than assuming we are working on a hypercube. A hypercube is a very restrictive space, where an unbounded space is much less restrictive. And so we're going to recover the same sorts of properties that we had for the Fourier series in differential equations and derivatives, but we're going to do it now for the Fourier transform. And it's going to be much more applicable to us with the rest of the semester involved. So I've got the same sort of proposition you saw in the last video, which is if I have a function which I'm representing as the inverse transform of a Fourier transform, inverse transform of Fourier transform. So I'm just, representing it as reconstructed from its own Fourier transform. I can then take a derivative of it in the j variable by exactly adding I times the j power, the jth component of y to the kth power. So this is the same sort of property we saw before, is that derivatives in the regular space are now powers in the Fourier space. And we can do the same thing as before with gradients, and that powers of the gradient are powers of the vector in the Fourier space. So this is the same idea of diagonalization of the derivative, and the proof is the same before. And before I get into some examples here, because I'm going to get into examples of how these derivatives play roles in the Fourier transform, I've got a remark about the variables in the natural space and the Fourier space being arbitrary. Okay, so we've used this boldface variable x to be the d-dimensional vector in R. We've used the boldface y to be the d-dimensional vector in the Fourier space, right? So we're like translating between x vector in regular and y vector in Fourier. And then you can, of course, reconstruct when you use the reconstruction and go back and forth between them. But those choices of x and y are super arbitrary. And so I want to comment here that just some of the common choices of a regular space are x compared to y in the Fourier space, or x compared to, this is actually, it looks like a w, it's actually lowercase omega. So that's x and omega as paired variables between the regular and Fourier space, or x and xi, which we encountered in the last video. Or we could actually have in higher dimensions x and y as vectors, or x and xi as vectors. So I just want to make it clear that the choice of these variables is very arbitrary, and you'll see all sorts of these variables in different textbooks. You just have to be aware that they get switched up on you a lot. And in the following examples, I'm using x and y in R2 as our natural variables. And then I'm using z and w in R2 as our Fourier variables. Okay, so we're jumping from x, y in the first set of variables, and then I compute a transform, and I end up with zw. And then we could go back to x, y, or we could go back to zw, and so on. So we just have to be aware that we can make those choices ourselves. And I'm going to be doing x, y, and then zw. So these examples are going to be very similar to the examples we had before. I had to modify the functions that we're looking at. Right, this is a slightly different function than what we're looking at because I wanted our functions to be square integrable. We have to remember square integrability. And hey, what do you know? The Gaussian showed up. So there's the two-dimensional Gaussian for us. But imagine somebody asked us to compute 4 derivatives in x and 3 in y of the following function. That would be something like partial x to the 4th, partial y cubed. You would not want to do that by hand. It would be really annoying to do that by hand. Instead, suppose somebody gave you the Fourier transform of this function. And that Fourier transform is I cosh z sinh w, and then a Gaussian in z and w. Now, this may be a lot of people's first experience with the cosh and sinh functions. I just want to cover them really quick. These are known as hyperbolic trig functions. They result from really Euler's formula applied to, you'll recall how cosine of x was like e to the ix plus e to the minus ix over 2. Cosh is the same thing, but imagine I got rid of the i's. So if I grab my eraser and just get rid of the i's here, that's cosh. I just add an h to get rid of the i's there. So cosh is that sum on the exponentials. Sinh is very similar, where sine originally started with e to the ix minus e to the minus ix over 2i, and then when you pay the price of removing the i's, you just say, hey, that's cinch. Okay, so these are the hyperbolic trig functions, and it allows you to use purely real exponentials to define these things. But anyway, so that's the Fourier transform here. And if we're going to compute some derivatives of this Fourier transform, our life gets pretty easy, right? So if I want dx to the fourth dy cubed, all I have to do is, boom, x to the fourth y cubed. Now, keep in mind there are some i's sitting around, right? So there's an I here, an I there, and with the powers, they go to negative I, and I've just canceled that negative I with that positive I. So I simplified a few things to say that this is what the derivative is equal to, but it really does make your life easy to say, hey, the derivative is just the inverse transform of a couple powers of x and y. And so we really have translated our derivative back into numbers like we saw before. We can do the same thing with the inverse operators like I did before. This should not be a series anymore. It should just be the Fourier transform. We can do the same thing I did with operators like before. So really everything that I did before, but now I'm doing it with the Fourier transform instead of the series transform. Imagine if I have this PDE and I really want to find psi. What I want to do is invert that operator. Right? I want to invert the operator and act it on the right-hand side. Once again, I'm notorious for having typos. This should be e to the minus x squared plus y squared over 2. But you can just imagine you just want this inverse operator well defined here. You can do it with the Fourier transform because the transform transforms, I wonder why it has that name, transforms the derivatives into numbers, really functions, right? They're functions of z and w. But it transforms these derivatives. There's a z squared, a zw, and a w squared, and then a couple i's give me the negative signs. If I want to take its inverse, I'm literally just taking 1 divided by those. And so this is kind of that whole freshman's dream that I was complaining about a couple class periods ago, where I said, phi inverse is not 1 divided by phi. Well, it kind of is as long as you're in the Fourier space. As long as phi is a derivative and you put yourself in the Fourier space, the inverse truly is a reciprocal. And that's what makes our lives really easy with the Fourier transform. And once again, just like before, we can do the same thing with exponentials. Imagine if I wanted to exponentiate dx squared plus dy squared. This doesn't really make any sense until you send yourself into Fourier space. And once you send yourself into Fourier space, what is dx squared in Fourier space? It's just negative z squared. Dy squared is negative w squared. And so you know exactly how to take that exponential. Anyway, that's all I've got for today. We're going to actually get into computing these using a Fourier transform table in the next class. So I'll see you then. Bye.